Communication codes are a nightmare to most technicians and mechanics out there. And this is mainly because most have been programmed to think that canbus communication is very complex and hard to understand. And because of that fear, most end up replacing modules that are actually in good condition, only to realize later that the same codes are reappearing. In this video, I'll be covering the basics of CAN communication network, and we shall be able to look at the various faults that can be encountered on the CAN bus and how we can test for those faults. Now, this will not only save you time, but also your money that would have been spent on replacing a module which is already working. Lloyd Steven is my name, and I'm the head technician at Nana Auto Diagnostics. And I want to welcome you to part 4 of our 7-part series that covers automotive communication networks. With the increase in the complexity and data speeds that are required in vehicle systems, the previous communication protocols such as the G1850, PWM and VPW, the K-line and the LIN could not match the demands. So CAN was developed and implemented to overcome the challenges that other previous systems or communication networks could not address. So we shall begin our discussion today by defining CAN bus communication. Now, CAN stands for Controller Area Network and is an automotive communication network that allows several control units or modules to communicate with each other without requiring a central computer. These are some of the characteristics of CAN bus communication. It's a broad type communication, meaning all devices or nodes can hear the transmission. Nodes can be added at any time, even when the network is operating. Now that is known as hot plugging. It uses differential signals and it employs a twisted pair of wires, which we know as CAN high and CAN low, mainly to reduce the noise and electromagnetic interference. And as the name suggests, it uses a bus topology. It also employs half duplex as a mode of communication, meaning transmission can only be in one direction at any given time. It also employs voltage states and relies on a recessive state, which is idle, and that is the same voltage on CAN high and CAN low, and a dominant state or the active state, which employs a voltage difference between CAN high and CAN low, which is 2 volts. We shall be able to look at that later on in our discussion. And then the standard speed for CAN bus communication can go up to 1 megabits per second. And the newer variations such as the CAN FD, FD standing for flexible data rate, can support higher speeds of up to 8 megabits per second. And lastly, CAN bus communication is asynchronous. If you don't understand some of these terms that are employed in this description, I made a separate video on the terminologies that are used in automotive communication networks. You can check it out. I will tag its link in the description below. If we are to understand how communication is achieved on the CAN bus, we need to understand a few parameters, and one of those is the termination resistance. So what is this resistance we are talking about? Now, on any given CAN bus, we have modules, or we can call them nodes. So if I have one node here, node 1, say node 2, and node 3, I'll treat this one as CAN high, and this would be my CAN low. Now these are the two twisted wires, and usually they are twisted to minimize electromagnetic interference. Remember, this is a differential signal transmission. In other words, if we have a voltage, let me say we are transmitting a 5-volt signal here, and we encounter noise, let me say of 1 volt, it will raise this voltage to 6 volts. And if on CAN low, we are transmitting, let me say, a 3-volt signal, and we encounter still the same noise, electrical noise of 1 volt, this will sum up the entire signal voltage to be 4 volts. So if we are transmitting only this voltage here, this noise, electrical noise, will be included in that signal. However, with CAN bus, we are transmitting a differential signal. In other words, we are getting the difference between CAN high and CAN low, and we are transmitting that result. For instance, here it will be this whole sum, which will be 6 volts minus 4 volts, giving you 2 volts. So we shall be transmitting the 2 volts instead of the individual voltages on the bus. So in case we encounter any electrical noise, see on either wires or on either lines, that will be cancelled out, because we are transmitting the difference, not the voltages on the individual wires. So that is why this communication network is relatively noise tolerant as compared to other networks. So at the end of the CAN bus, we expect to have terminal resistors. Let me call this R1. Let me also call this resistance 2. Now these are known as the terminating resistors or terminal resistors, and they are usually of 120 ohms. Now, what is the use of these resistors? The main use of these resistors is to prevent signal reflection. In other words, whenever we have signals being transmitted along these lines, if they are not absorbed by any resistors, they will be reflected back. And once they are reflected back, they're going to interfere with the actual data that is being transmitted on the bus, and that will result into communication errors on the bus. So the main importance of these terminal resistors is to prevent signal reflection on the bus. These resistors are very important when it comes to diagnosis of any CAN bus. And they are usually located within modules. You may not find any resistor hanging outside, but it will be incorporated or found within the module itself. Some of these modules may include the ABS module, the instrument cluster, the engine control modules. You can find it in the TCM. So it is always advised to check your wiring diagram to be able to find exactly where these resistors are located. So why am I talking about these resistors? When it comes to diagnosis, you can be able to tell, depending on the resistance on the CAN bus, whether the terminating resistor is shorted or it is missing all the lines CAN high and CAN low are shorted to each other, or there is an open on either line, depending on the value of the resistance that we measure on that bus. And usually this is measured from the OBD2 port. Now CAN high is on pin 6 on the OBD2 port, and CAN low is on pin 14 on the OBD2 port, or most know it as the DLC, which is the data link connector. So what happens is, if you get your multimeter and try to measure for the resistance between CAN high and CAN low from the OBD2 port, if the network is healthy, you get the effective resistance of these two resistors. And as we can see from here, if you're measuring from these 2 points, these resistors, they are in parallel. And we know that if you want to obtain the effective resistance, it will be 1 over R, which is 1 over R1 plus 1 over R2. If you want to know the resistance that we shall be having here at the DLC, if this system is healthy or normal, we shall have to compute for the effective resistance of this entire network. So this effective resistance will be equivalent to 1 over 120 plus 1 over 120. So this R will be 60 ohms. So whenever we have a healthy system, the resistance here will be 60 ohms at the DOC. Or if you remove one of the modules and also measure at CAN high and CAN low, you always have 60 ohms. So what will be the implication if you end up with 120 ohms when measuring between CAN high and CAN low? If you obtain 120 ohms, it implies that a module that is containing one of the terminating resistors is not being recognized on the network. Either we may be having an open on that exact module, or if it is unplugged, we shall be only reading one resistance value. So we shall be recording only 120 ohms. So it can either be this one or that one. So whenever you encounter a 120 ohm reading on the CAN bus, just know that one of the terminating resistor or module containing that resistor is missing. On the other hand, if we have 0 ohms, what is the implication if we end up with 0 ohms? Now, if you have 0 ohms, it implies that CAN high and CAN low, they are shorted to each other. So that is another scenario that you can encounter. Whenever we have CAN high and CAN low shorted to each other, the resistance value between them will be around 0 ohms. How about if we have an open in either can high or can low or in both communication lines? Whenever we have an open, we shall always have an infinite value or a value in mega ohms. A very big value of resistance will be recorded whenever we have an open in either can high or can low, or whenever we have an open in both communication lines. So in summary, whenever we have 60 ohms, that is a normal reading showing that the circuit is okay. If we have 120 ohms, that is an indication that one of the terminal resistors is not being recognized on the network. So one terminal resistor is missing. So you have to check out which module contains that resistor. The other scenario is when we have 0 ohms. If you have 0 ohms, it means can high and can low, they are shorted to each other. If we have a very big value in mega ohms or an infinite value, it implies we have an open in either can high, can low, or in both communication lines. Next, let's talk about how signaling is attained on a canbus communication network. And we shall begin by identifying the logic states. Now in communication, we have 2 logic states, which is logic 1 and logic 0. As pertains to canbus communication, a logic 1 is considered as a recessive, and a logic 0 is considered as a dominant state. What do I mean? If you have 2 nodes, node A and node B, node A transmitting 4 bits, which is 1, 1, 0, 1, and node B transmitting 1, 1, 1, 0. So node A will be given precedence over node B. Why? When you look at the first bits, they are all the same. The second ones are also the same. When we come to the third bit, node A is transmitting a 0. Node B is transmitting a logic 1. So a logic 0 is dominant over a logic 1. So if these 2 nodes are transmitting at the same time, node A will be given precedence over node B. So the data for node A will be transmitted first, and then later node B can transmit its data. So that is what it means for a bit to be recessive and the other one to be dominant. So bit 0 is considered to be dominant, and bit 1 is considered to be recessive. Now with that in mind, let's go ahead and explain how we can obtain a logic 0 and a logic 1 on the CAN bus. When it comes to CAN bus communication, whenever the system is at idle or recessive, so to say. Both can high and can low, they sit at a voltage of 2.5 volts. Now whenever we have communication on the bus, can high we raise to a voltage of 3.5 volts and then drop down to a voltage of 2.5 volts. So in other words, can high oscillates between 3.5 and 2.5 volts. On the other hand, can low oscillates between 2.5 and 1.5. So this is can low, this is can high. So this is oscillating between can low between 2.5 volts and 1.5 volts, whereas can high is oscillating between 3.5 volts and 2.5 volts. So we shall have oscillations in that range of voltage. So what happens is, whenever the system is at idle or don't have any transmission on the system, can high and can low, they both sit at a voltage of 2.5 volts. So when you get the difference between can high and can low, we shall have 2.5 minus 2.5, which will give us 0 volts. Now the 0 volts, whenever we have 0 volts on a canbus, that is considered as a logic 1. Now the 0 volts, that is a logic 1, meaning the system is recessive or it is passive, so to say. That's why we have our recessive state here as a logic 1. In other words, we don't have any transmission on the bus if it's idle, and that occurs when the voltage difference between can high and can low is 0 volts. On the other hand, when you look at can high and can low, when the bus is active, when you get to the difference of can high, can low, can high here sits at a voltage of 3.5 and can low sits on a voltage of 1.5. This will be equivalent to 2 volts. Now whenever we have a difference of 2 volts on the CAN bus, that is considered a logic 0. And a logic 0 is a dominant logic state on the CAN bus. So in simple terms, at that point, the bus will be active. Whenever we have a logic 1, which is representative of a voltage difference of 0 volt, the bus will be recessive or passive, so shall not have transmission on the bus. We shall be able to look at these waveforms on the oscilloscope, and we shall be able to simulate different fault codes, such as can high short to ground, can high short to power, can low short to ground, can low short to power, can high and can low short to each other, open circuits on can high and can low, and on both. We shall see what happens when can high and can low are shorted to each other, and observe those waveforms practically. So keep yourself on the channel, more is coming. If you have not yet subscribed, subscribe, turn on that notification bell, like, share. Thank you for watching, and in our next video we shall be looking at flex ray.